I'm here today to speak to you about Raft and distributed systems, but first I'd like to thank the organizers and sponsors of PyGotham for making this conference possible. So many of the systems we depend on as a modern society, like hospitals and banks, credit cards, stock exchanges, and airports, all need highly reliable and available computer systems to work. Unfortunately, single machines are not up to the task. They're susceptible to crashes and downtime and need maintenance. The solution, of course, is to have multiple machines doing the same job. But how do we get them to do so? This is not a simple problem. The network connections between the machines are not reliable, the machines themselves may crash, and we don't want to involve people to fix things because nobody wants pager duty to go off at 3 a.m. on a Sunday. So a consensus is a fundamental part of building replicated systems and getting these machines to work together. The idea of getting them to work together is to have them all store the same data or commands in their logs. This increases the overall system reliability because if one machine fails, another machine can take up its work. So in this talk, I'm going to cover naive solutions to consensus and why they fail, give a tour of Raft, which is a more sophisticated and fault-tolerant system, which is resilient to several different types of failure, and then I'm going to touch briefly on Paxos and implementing Raft in Python. So to be correct, a consensus algorithm must display the following properties. Agreement, in which every correct process must agree on the same value. Validity, the value agreed on, must have been proposed by another process, so we can't have the individual participants making things up or only storing none. And termination, where every correct process eventually decides on a value. Another important theorem in consensus is the CAP theorem, which states that it's impossible for an algorithm to provide more than two of these three properties. Consistency, where every read receives the most recent write or an error. Availability, where every request receives a response, but there's no guarantee that it's the most recent. And partition tolerance, where the network continues to operate despite delayed or lost or dropped messages on the network. So let's review what could possibly go wrong. There's the fail, stop, or crash, where a participant does not recover and does not rejoin the cluster. Fail, recover, where a participant leaves the cluster, but returns after an arbitrary time, which could be caused by processing delays, networking delays, or network partition. Network partition, where a cluster participant is separated from the others due to failure of part of the network or a change in network topology. Or a Byzantine failure, where a participant exhibits arbitrary or malicious behavior and sends contradictory conflicting data to the other participants. So Byzantine failure got its name from a computer science paper in which 9 generals surround a city that they want to attack. But they can only take the city if they all agree to attack at once. The messengers that they send between them are flaky. They may get lost or captured. But one of these generals is a spy and will try and sabotage the other general's plans. This general may send an attack vote to 4 of the generals planning to attack, or a retreat vote to the 4 generals planning to retreat. In this example, the traitorous general is the machine sending the contradictory or conflicting information to the other participants, and we'll see how Raft can recover from some instances of that. So I'm going to use the terms from the Raft paper. The terms in distributed systems can get a little overloaded and it can be difficult to see what people mean. So in this case, the client sends data, and it's not a participant. The leader accepts data from the client, and the leader sends data to its followers. All data flows from client to leader to follower. And in each participant, the log stores the data. It acts as the state machine. The aim is to have the logs match, and in my examples I've used numbers as the items that logs are storing, but they can also represent database writes or machine commands that all machines have to execute. So let's take a look at a simple consensus system and see what happens. So this and the following example are all synchronous systems. So they all send the messages in rounds, like taking turns in a game. And the leader will send messages to its followers, wait till all the followers have responded, and then send the next round of messages. So in two-phase commit, the leader sends a prepare to commit message to the followers respond, and then the leader sends a commit message and the followers respond, and they all commit the data at the same time. So let's see what happens when the leader fails. So in this case, the leader has failed while sending a commit message to the followers, and some of the followers have received it and one has not, and someone's pager has gone off. So let's take a look at a system where one of the followers can step in and act as the leader when the leader has failed. We're going to do this by adding a second round of messages, and this second round of messages transmits the agreement to the entire cluster that they've all agreed to commit, but don't commit yet. And then when that message has been confirmed by all the followers, then the leader sends out the commit message and we all commit. So let's see what happens if the leader has a fail stop. In this case, the leader has received affirmation from the first message. All the followers have stated that they're prepared to commit. The leader then sends its message to the cluster that everyone has prepared to commit. Then the leader crashes and doesn't see the confirmations from the follower. One of the participants helpfully wakes up and says, "We've all prepared to commit. I'm going to go ahead and send the commit message now." But then the leader suddenly wakes up and sees that it hasn't received all the confirmations and aborts the transaction. One follower gets that message, one follower gets the message from the other leader, and somebody's pager goes off. So let's take a look at Raft. Raft is another consensus algorithm that was created by Diego Ungaro at Stanford in 2014. It decomposes consensus into leader election and log propagation phases. It is asynchronous, so there are no bounds on when a message might be sent or a response received, and so it's hard to tell if a participant has crashed or if it's slow. And we'll see that it actually doesn't matter in Raft if a participant has crashed or is slow. And now I have to warn you that asynchronous consensus algorithms with one faulty process may never terminate, according to the FLP paper from 1985, but we'll see, like Wikipedia, that this works in practice but not in theory. So Raft has an overall rhythm of log propagation punctuated by leader elections. A term is important in Raft. They act as a logical clock and increase monotonically, and each term is an election followed by a period of log propagation. The messages in Raft are not time-stamped, but they do indicate what term they were sent in. Leaders in Raft serve until they fail, and that triggers a new election, and the cluster does not accept data from a client during the election phase. So this is our Raft cluster. The participants are all identical, and any of them can serve as leader if their logs meet certain conditions. They all start as followers, and we'll see how this allows Raft to recover from network partitions and participant failures, and it's resistant to fail recover and fail stop of any member of the cluster. So now we've run an election, and we have one of the followers has timed out and reached candidate status. Each follower in Raft has a random election timeout, and this is to prevent all of the followers from turning into candidates at the same time. The followers will start elections unless they do not receive a heartbeat or append entries message from a leader within the minimum election timeout. If the leader discovers a follower with a larger term, it updates its term and reverts to follower. And elections all have to happen within the span of the shortest election timeout of any member of the cluster. So to start an election, a follower times out, votes for itself, and then sends a vote request to the other followers. If the followers have not voted in the current term, they vote yes. If they have voted, they vote no. And if follower logs are longer than the candidates or at a higher index, they also vote no. If the followers have heard from a leader via a heartbeat or add entries message within the minimum election timeout, they also vote no and do not update their term. And for the timing requirement for what these timings are, it depends on how your cluster is set up. The time it takes for a leader to send messages to its followers must be an order of magnitude less than the election timeout, which should be a few orders of magnitude less than the mean time between failures of the participants in the cluster. So now we have our leader, and the leader is the only participant that can accept data from the client. If the followers hear from the client, they redirect to the last leader they heard from. The commits in Raft are two-phase. A leader proposes a log entry to the followers. When a majority of the followers have responded, then the leader sends a commit message. Messages in Raft are idempotent, and you can send the same message multiple times and will only have effect once. The messages all contain information about the leader's log, a new entry and the entry in the leader's log preceding it. Leaders never delete data from their logs, they can only append. Followers can't change the leader's log, and if the leader doesn't hear from the client for a time, it sends heartbeats to which the followers respond. Now, the followers have a couple actions they can take when they received an add entries message from the leader. They can accept the entry. They can ignore any accept entry message from a leader that contains a log entry they already have or from a stale term. If an entry has a higher term, the follower updates its term to match the term number in that entry. And if the log entries don't match, the followers can reject them. And the leaders respond to reject entries from followers by going back through the leader log, sending add entries message until they find a point where the leader and follower logs match, and then the leader deletes everything in the follower's log after that, and then sends add entries messages to catch the follower up. So this prevents some type of Byzantine failures, and also you can just chunk a new follower in, and it will be brought up to speed by the leader. So this is an example of a vote message. It contains who it's from, who it's sent to, the length of the sender's log, the term, and a value for the vote. This is an add entries message. It contains who it's from, who it's sent to, what their status is, what term they think it is, whether to commit or add to the log, the success message that the follower can set when it responds with it, the index of the last log entry, and the new log entry. Logs in Raft are governed by a principle called log safety. If two entries in two different logs have the same index and term, they store the same data. The leader creates at most one entry with a given log index during a term. Log entries never change position in the log, and if two logs have an entry with the same index and term, the logs are identical in all entries up through the given index, which is how the leaders can go back to the follower logs that have something missing, delete everything else, and they'll match. There's another property in Raft called leader completeness, and this is enforced by having the followers vote no for candidates that have short logs or logs at a lower index. Since commit messages are confirmed by a majority of the cluster, an entry must be stored on the majority of the participants, and this selects for leaders with the longest and most complete logs because the leaders can't get elected without a majority of the cluster voting for them. Now, despite the random election timeouts in Raft, you can get into a situation called a split vote, where you have two candidates that time out at the same time. Because there are no leader can get elected at this point. Neither of these candidates can become leader. What will happen is, because no heartbeats are being sent, one of the other followers will time out, send their vote request to the rest of the cluster, and that will be elected leader. Raft can also automatically recover from a network partition. We'll see in this example that two of the participants have been separated from the rest of the cluster, and one of them has timed out and started an election. What will happen when the partition is removed is that the leader will send either a heartbeat or an add entries to those followers. The candidate will revert back to a follower status, and the leader will catch up the candidates if they've missed any add entries messages for their logs. Now, if you have your Raft cluster running for a while, logs can get kind of long and unwieldy and difficult to store. So the algorithm actually makes a provision for snapshotting, which allows the entire log to be written to stable storage. Snapshots contain metadata about the last term and the last index of the last log entry in it. They can be sent to new or slow followers to catch them up as a single chunk of data. And followers can snapshot at any time, and they don't need leader permission to do it. Raft also has the ability to have drastic changes in membership, and the cluster still keeps working. Because it may be necessary to add or remove large numbers of participants for config changes, updates, or maintenance, this property prevents there from being two majorities of participants that will elect different leaders. So log entries are sent to and committed by both clusters during this process. And a participant from either cluster can serve as the leader. The agreement on elections and entry commitment requires majorities from both clusters. And since it can take time to swap out participants, the entire thing keeps working while this is going on. The way it works is that a config message called old new is sent and committed by the leader. And even if this leader fails once this message has been committed, a follower with only the new config cannot get elected as leader. Once the leader sends out a message new, it can step down as leader and the new config will run a new election. And once the new message is committed, you can start shutting down the old cluster. So, in order to get data out of a Raft cluster, the leader sends a round of heartbeats to which the followers respond to confirm it's still leader, and then it responds to the request from the client for data. So now we've seen how Raft can recover from participant failure, participant fail recover, and network partition. Having the leaders correct the followers' log that don't match their own prevents some instances of Byzantine failure, but it's recommended that you run Raft in safe network environments. So Raft can be implemented in Python using just the standard library. It is asynchronous. You have to use either async.io or Curio. In the project I'm working on, I used Curio because it has excellent documentation and examples. The participants I set up as class objects, and I pass messages between them as a queue, but you could also use sockets in order to do that. So now we've gone through all this technical stuff, and I think we all deserve a vacation. So let's take a little trip to a Greek island. So Paxos is named for the Greek island. It is an early proof of safety in a fault-tolerant distributed consensus protocol, and was first created by Leslie Lamport in 1998 in a paper called The Part-Time Parliament. It was called this because he used the idea of a parliament with a bunch of parliamentarians that wander in and out at random times. They all communicated by messenger, but the messengers would sometimes leave also. So he would sometimes get dressed up as like Indiana Jones in order to give this talk and pretended that he discovered this system of government on the ancient island of Paxos. Raft was created in reaction to Paxos, and Raft is intended to be more understandable than Paxos. Raft is designed to be as safe as Paxos in the sense that it can guarantee that something bad will never happen. And Paxos is actually very narrowly focused on the process of getting all the participants to agree to store the same values. It doesn't address things like how the participants are supposed to get caught up if they don't have missing log entries. It doesn't cover things like membership changes. So Raft is kind of more practical and engineering oriented, and Paxos is more academic. And also the leaders in Raft are clearer. In Paxos, you can have any member of the cluster send commit messages to all the others, and if the majority of them respond, then it's committed. And some of that carries over to Raft, but yeah. So thank you very much.